presentation. I am Nam and with me here are Tung and Huang, and we are group 16. Our project is smart system under passive interface sensor to control fan and light in smart home. The system consists of two devices, a computer and a DAQ USB 6255 device. The computer will acquire sensor data, process and send signal to control the DAQ device. DAQ device is used to read passive interface sensor via data control LED and fan. On computer, we can control DAQ device in three modes: schedule mode, manual mode, and real-time mode. Here we create a simple circle that reads the PR sensor input in terminal 1. AI0 of USB 6255 fan and LED are controlled by analog output terminal A0, A01 respectively. We use LM298 DC motor driver control to amplify the signal from DAQ to 9 volts and use to it to control the fan.
The user interface in UI main VI file can control every function of this project. It's contained two parts: control panel, a panel on the left and tabs on the right. The control panel displays status of the program and control flags manually. The tabs contain new feed data from JQ, TCP server, and um, client information, ORM module, and schedule mode control. User can control flag manually by drag and drop the fan speed slider and LED knob in control panel. New feed tab show latest 100 data points in real time. PR wanted is then draw data from JQ. PR sensors show processed sensor data 1 means faster. The thread show 0 mean below. Fan speed and net graph show output data. History tab show all data from current session. It can also save and load data. On schedule tab, user can create, modify, delete schedule. After created, the schedule will appear on the pending list below in uh, ex- execute time order. Switch on enable button will change programs to schedule mode, and each pending schedule will display their time till activation. TCP tab shows transmission control protocol collection status with Python server and LabVIEW. Optical rec- recognition model tab show video stream from Python server. Configuration tab contain all settings available. GQ device and PIR input terminal choose PIR threshold time before fan turn off.
The main program is a flash sequence structure. It contains three frames executed in order from left to right. The first frame is to set up all required variables for each run. This frame can run each time the user presses the run button, and this also sets the default mode to real-time mode. The second frame is to check the DAQ connection, determine whether the run is in simulation mode or not. It tries to send a signal to turn on flash to the DAQ. The error out from DAQ write to simulation check to handle the error. Inside the last frame is for case structure. When the user runs the program, the first three cases will execute in parallel with each other. Case 1 is for computing and process schedule. It calculates schedule time, sort the schedule table, and calculates the remaining time. Case 2 read the sensor data continuously. The data from DAQ was then sent to three independent sections. Manipulate output sub-VI, serve waveform on LabVIEW tab, and save data on History tab. Manipulate sub-VI handle everything needed to control light and fan. Case 3 is TCP client data handling block. This case controls all TCP data in and out from the server to LabVIEW client. Each time we receive data from the server, we need to check for error in connection and data integrity. After verifying the data, OK code is sent back to the server. If we discover any error with the connection or the data doesn't match, TCP connection is restarted. Ping graph is calculated by subtracting the time when command ends with the time command starting time. Error rate is the time connection restart per 2000 ms. TCP restart procedure described by below.
Example. To run the program in real-time mode, make sure USB 6255 device is connected and configured in L and E mode. Next, navigate to Configuration tab and select device in and PR channel, then click on Run. The program will automatically start in real-time mode.
While on real-time mode, you can switch to manual mode by clicking on override reason button when manual mode is enabled. Enable night on the left of override reason button will change to green and status state in a control panel will change to manual mode. To turn off manual mode and return to the previous mode, click on the button again.
Schedule mode. To create a new schedule, navigate to Schedule tab. On Set a new schedule section, change the time to the time you want to run the action, and then choose when should it repeat and what action to run. Each schedule will be given a unique ID. Enter the ID in config schedule section and press enter. To enable the schedule mode, click on Enable button on Schedule tab. The mode on the control panel will be updated. Running the optical recognition module. After verifying that a correct version of Python is installed, click on Start Server to start the Python script and then navigate to TCP tab. When the server light indicator changes to green, we can connect it by press on Connect button to connect with Python with LabVIEW. Then you can start navigate to ORM tab to see visual feed and value received from the server.
Performance analysis. Because of the scale of the project, performance is a very important factor of our program. On LabVIEW, we can implement the non-blocking wait method for all functions that require timing such as scheduling, writing, reading the query data, real-time flash control. Implementing sub-VI also an important factor. On Python server, treating it used to run ORM server handling in parallel. Because we are short on time, we couldn't optimize the Python server much, so the setup time is somewhat slow, about 11.2 seconds. We could try to optimize this in the future.
After not of discussion, planning and programming, we successfully created the SSICFL. The system is up and running perfectly on our machine and controlled net and fan. smoothly, although the ORM still has some trouble connection and some optimization need to be done. We still consider to this project is finished. In original idea, we also thought about a new module, the Google Assistant Controlled Module, GAC. This module creates a device called Flat, Fun and Net, and as another way to control DAQ from smartphone device. We successfully created and connected the module to Google Cloud and set up another server port for handling requests from Google. But due to the deny, we cannot finish it in time. Yeah, thank you for listening to my video.